So I gave you a definition of second normal form. Here it is again. R is in second normal form if and only if for every key k of R and every non-key attribute A of R, the functional dependency k arrow A, which certainly holds, is irreducible. That is a correct definition. There is another definition, which I'm going to claim is equivalent. I'm not going to attempt to prove it. It's an interesting exercise to try and prove it, but I will simply state it. R is in second normal form if and only if for every non-trivial functional dependency x arrow y that holds an R, either x is a superkey, or y is a subkey, or x is not a subkey. What the devil is all that about, I hear you cry. Clearly this requires some explanation. All these terms in green here are terms I have not previously defined. Let's take a closer look. First, a functional dependency is trivial if it can't possibly fail to hold. Let's look at this relvar here once again. There is a functional dependency from city to city. If two tuples have the same value for city, they have the same value for city. Right? There's nothing you can do about that. You can't possibly not have that functional dependency hold. Come to that, city and status together, arrow city. If two tuples have the same city and status, they certainly have the same city. So an FD is trivial if it can't possibly be violated. In fact, it's easy to prove that a functional dependency is trivial if and only if the right side is a subset of the left side. Like S number, P number, arrow, supply number is trivial. Come to that S number, arrow, S number is trivial. Trivial FDs are not very interesting, of course, because they're trivial. When we're doing database design, we typically don't bother to think about trivial dependencies because they're trivial. But if we're trying to develop a theory, we have to take into account all possible FDs, trivial ones as well as non-trivial ones. Okay. So I kind of mentioned this just to get it out of the way. Backing up for a second, my alternative definition of second normal form talks only about non-trivial functional dependencies. So there are trivial dependencies as well. You can never get rid of those. They're always there. There's nothing you can do about them. And what's more, they don't hurt. So that's what trivial is about. What's a superkey? Loosely, it's a superset of a key. So, for example, the key here is supply number and part number, but supply number, part number, and city is a superkey. So a superkey for relvar R is a subset, let's call it SK, of the heading of R that has the uniqueness property, but doesn't necessarily have the key irreducibility property. Which means all keys are superkeys, but most superkeys are not keys. And a superkey that is not a key is sometimes said to be a proper superkey. Well, now, you see, I said before that you always have arrows out of keys. That's true. More generally, you always have arrows out of superkeys. Supply number, part number, and city is a superkey here, and there's an arrow out of that to everything. If two tuples have the same value for supply number, part number, and city, they have the same value for everything, because they're the same tuple. So there are always arrows out of superkeys. You can never get rid of those. So backing up again, one of the possibilities is that the left-hand side in the functional dependency x arrow y is a superkey. Question for you. Our familiar suppliers relvar has just one key, supply number. How many superkeys does it have? Not one. It's been a long day, I know. It's 8. Clearly, supply number by itself, the key, is also a superkey. Then you can combine supply number and name, or supply number and status, supply number and city, they're all superkeys. Or you can combine supply number and two of the other attributes, name and status, or status and city and name. and then the entire heading is clearly a superkey. As a matter of fact, the heading is always a superkey, always. So that's what a superkey is. It's, loosely speaking, a superset of a key. A subkey, of course, is a subset of a key. So, for example, supply number and part number is a key. Supplier number by itself is a subkey. All keys are subkeys because every set is a subset of itself, but most subkeys are not keys. And a subkey that is not a key is sometimes called a proper subkey. So you can guess the next question. Think of our familiar shipments roll var with supply number, part number, quantity. It has one key. The combination supply number and part number. How many subkeys does it have? Three? Four? Four is right. Supply number and part number is a key, a subkey. It's also a key. Supply number by itself is a subkey. Part number by itself is a subkey. And don't forget the empty set. Every set has the empty set as a subset. So the empty set of attributes, in fact, the empty set is always a subkey for every possible rel var. So here again is the definition. R is in second normal form if only if for every non-trivial fd x arrow y that holds in R, x is a superkey, or y is a subkey, or x is not a subkey. Trust me, these two definitions are equivalent. It's a bit non-trivial to prove that, but it is in fact true. So, do I have a slide on this? No. If we again look at our example here of SPCT, we have this functional dependency supplier number, part number, arrow city. That is a functional dependency that holds. But in that functional dependency, I beg your pardon, supplier number, arrow city is the one I wanted to talk about. Start again. Supply number arrow city is a functional dependency that holds. But in that FD, the left-hand side is not a superkey, so property A fails. The right-hand side is not a subkey, so that one fails. And the left-hand side, is a subkey, so that one fails. So all three of these fail, and therefore this is not in second normal form. Now, there is a reason that I've given you this much more complicated definition. It's going to turn out to be important when we look at third normal form in a little while. Yeah?
I'm sorry, does it hold if A, B, and C, or A, B, or C?
So or.
Oh,
yeah.
it says or.
Yeah.
Okay.
Yeah. At least I got that one right. Yeah.
Can I have you repeat that question, please? Kirsten, could you go in on a close-up, please?
It's not necessary. It's
No.
kind of obvious.
Okay.
I'm actually kind of
One more
embarrassed.
time.
It's nice that sometimes the answer's on the slide.
Just stay in there, Kirsten.
Right on my face. Awesome.
Can we go on? All right. So what about third normal form? We talked about second extensively. What about third? Again, I have a poster to illustrate this one. There it is. Again, I'm going to start with my regular example of suppliers, but I'm going to make a semantic change, a change in the predicate, if you like. I'm going to assume that the functional dependency city arrow status holds in rel var s. That means if a certain supplier is in London, they must have status 20. If they're in Paris, they must have status 30. I've made a change to the value to be consistent with this new constraint. Okay. If you're in Athens, you must have status 30. So we have a functional dependency from city to status. And let me just tell you, informally, you can see this is bad because this is a functional dependency that is not out of a key. And that's what's going to cause the trouble. In fact, it does cause trouble because every time we see London, we see 20. Every time we see Paris, we see 30. We have redundancy again. And the solution, again, is going to be to break this down by taking projections into smaller ReLVARs of lower degree. So this is just the same as the poster here. Here's a definition of third normal form. R is in third normal form if and only if, for every non-trivial functional dependency x arrow y that holds, either x is a superkey. You can never get rid of arrows out of superkeys. Or y is a subkey. And here the problem is that x is not a superkey and y is not a subkey. So this one is not in third normal form. And if you compare this definition with the second definition I gave you for second normal form, it is immediately obvious that if you're in third normal form, you're also in second, because second normal form has condition A or B or C is another possibility, which I've now dropped. That was my reason for giving you that more complicated definition for second normal form. It makes it immediately obvious that third normal form is a special case of second normal form. Let me warn you, there is a massive confusion out in the popular literature around this area. Many definitions you'll find for third normal form in the literature are not definitions of third normal form. They're actually definitions of Boyce-Codd normal form, which I'll get to in a moment. So I'm just warning you. Well, the problem with this version of supplies is obvious. It's not in third normal form, though it is in second normal form. You can check the definition later if you like. It is in second, but it's not in third, because city arrow status holds, city is not a superkey, status is not a subkey, and that functional dependency is the source of the redundancies and therefore certain update anomalies, which I won't bother to go through. So the further normalization discipline says break it down, and we can use Heath's theorem to guide us on that. And what we'll do, in fact, is replace suppliers by one ReLVAR that has city and status, where city is the key, and the other one will have supplier number, supplier name, and city. And supplier number is the key there. And those two ReLVARs will in fact be in third normal form. And so finally we come to Boyce-Codd normal form, and I will now tell you, and you might be rather angry with me about this, this is the normal form with regard to functional dependencies. This is your target. So you may well ask, why on earth did I bother with all this nonsense about second and third normal form? Well, I'll explain that in a moment. Here's the definition. R is in Boyce-Codd normal form if and only if, for every non-trivial functional dependency x, r, or y that holds in R, x is a superkey. So the only FDs that hold with BCNF are either trivial, you can never get rid of those, or they're out of a key. You can never get rid of those. Well, out of a superkey, comes to the same thing. So in Boyce-Codd normal form, the only functional dependencies are ones you cannot get rid of. So you see, Boyce-Codd normal form in a way is conceptually simpler than all the other stuff we've been talking about. It just says there are no arrows, except the ones that are always there and you can't get rid of them. Some people like to remember this by this little catchy phrase. In a Boyce-Codd normal form ReLVAR, every fact is a fact about the key, the whole key, and nothing but the key. The first time I ever recited that line in a seminar, someone at the back of the room said, "So help me Cod." I wish I had thought of that. But I have to say that this characterization, although it's intuitively attractive, is not really accurate, because it does assume there's only one key, which is often the case, but not always the case. A better way to say it is the only arrows are arrows out of superkeys. That's more accurate. So you see, if you guarantee in your database design that all your ReLVARs are in Boyce-Codd normal form, you know that certain redundancies cannot occur. And you know that certain update anomalies cannot occur. That's why BCNF is a good target. Why is it superior to third normal form? Well, just compare the definitions. If you remember, third normal form had two conditions, A and B. We drop condition B to get to Boyce-Codd, which shows that everything in Boyce-Codd normal form is in third normal form. Here's the definition of third normal form. X is a superkey or Y is a subkey. If we drop that bit, we get a definition of Boyce-Codd normal form. So Boyce-Codd normal form implies third normal form. So let's look at a quick example of a Relvar that's in third normal form but not in Boyce-Codd. Again, I'm going to modify my running example for a moment. Let's suppose that supplier names are necessarily unique, so that supplier name is in fact a key for suppliers, as well as supplier number. Furthermore, let's suppose that we carry that supplier name attribute in the shipments Relvars. We have supplier number, supplier name, part number, and quantity. Well, do you see that there are two keys here? Supplier number and part number is a key, and supplier name and part number is a key. Right? There are two keys in this Relvar. And by the way, since there are two keys, I see no reason whatsoever to make either one more equal than the other, so I haven't chosen a primary key. I have no double underlining here, but that's a detail. So we have two keys. We also have, well, you can see the problem just by looking at a sample value. It says supplier 1 Smith, part 1, 300. Supplier 1 Smith, part 2, 200. Every time it says supplier 1, it says Smith. And every time it says Smith, it says supplier 1. There's all kinds of redundancy here again. And we have a functional dependency, supplier number, arrow, supplier name. If two tuples have the same supplier number, they must have the same supplier name. Also, supplier name, arrow, supplier number. If two tuples have the same supplier name, they must have the same supplier number. So those two functional dependencies both hold. And they're not arrows out of super keys, because these are the keys. These are actually arrows out of proper subkeys. So they violate the definition of Boyce-Codd normal form. On the other hand, the right-hand side of these functional dependencies is a subkey in both cases, so this thing is in third normal form. So this is in third, but not in Boyce-Codd. And therefore, the normalization discipline says decompose it. I'll do that in a second. Just a little remark here. It says there's some amusing history here. By rights, this thing should have been called fourth normal form. And it nearly was. When Raymond Boyce did the original work on this, he proposed it as a fourth normal form. But Ted said, no. This is what I meant when I defined third normal form. So Ted always called this third normal form. And everyone else in the world said, no, we can't have two different things both called third normal form. So everybody else called it Boyce-Codd normal form. The trouble was, by the time the importance of this one was recognized, there was already another normal form out there that was called fourth. So the name had been taken. So you couldn't call this one fourth. So this lies between third and fourth. It's 3.5, if you like. How do we break this down to get rid of the redundancy? There's two ways. We can break it down into supplier number, part number, and quantity, our usual shipments Relvar, and then supplier number and name. Or we could break it down into supplier name, part number, and quantity, and supplier number and supplier name. There are two decompositions, which does illustrate the point, by the way, that the decomposition in the normalization process is not necessarily unique. Sometimes you have to make a choice. And sometimes there are no good guidelines for making the choice, which illustrates the point that design theory is useful, but it doesn't answer all design questions. In fact, this normalization theory here is really important, but I would say it accounts for 15 or 20% of design problems, maybe less. A lot of database design, I'm sorry to say, is still subjective. We need more science. normalization is kind of the little piece of science that we do have. Well, okay, let me answer the question I raised a few minutes ago. Given that Boyce-Codd normal form is the normal form with respect to functional dependencies, which it is, why do we bother with second and third at all? Well, part of the answer is that it gives you some insight as to what goes wrong if you don't have Boyce-Codd normal form. See, another way to look at it is this. BCNF says the only FDs are out of keys, loosely speaking. How can a relvar violate that requirement? There are basically two ways. You can have an FD out of a proper subkey, or you can have an FD out of a non-key. If it's out of a proper subkey, it means you're not in second normal form, and if it's out of a non-key, you're not in third normal form. So second normal form and third normal form give you some idea as to what can go wrong if you don't go for BCNF. So that's one useful thing. And the second point is they do recap history. Because of course this was the order in which these things were historically defined. We started off with first, and then Ted Codd defined second, and then he defined third. In fact, Ted not only started the whole field of relational theory, he started the field of design theory too. He wrote the first paper on this stuff, which is pretty amazing, really.
Could you clarify the last sentence, please? FD out of non-key.
Yes, so this is one of the ways things can go wrong. In my example here, we have a functional dependency out of city aerostatus, and city is a non-key attribute, it's not part of any key. And it's that FD that causes the redundancy and causes the trouble. A couple of final remarks. BCNF is the final normal form with respect to functional dependencies, but is not the final normal form. There are other kinds of dependencies which lead to other normal forms. So this is a huge topic in its own right. Secondly, let me repeat something I said at the beginning. Languages like SQL or Tutorial D, the relational model, individual database management systems don't care what level of normalization a given relvar is in. If a relvar is not in Boyce-Codd normal form, that makes life harder for the user. It makes it harder to formulate queries properly. It makes it harder to formulate updates properly. It makes it harder to state constraints properly. But those are all user problems. Having the database well designed helps the user, and to some extent helps the system. But the user is the primary focus. So the higher levels help the user, partly because they make the database easier to understand. I mean, our running example, I'd venture to suggest, was very easy to understand. And one of the reasons for that is because it was properly designed. Might help the DBMS because it makes certain integrity constraints easier to enforce. But these higher normal forms are not required. There is a user choice, or I should say a designer choice. And my last point is normalization is a very important part of design theory, but actually there are other aspects to design theory in addition to normalization. So with that little teaser, I'm going to leave it there. That brings me to the end of the session on design theory, and indeed it's the end of my entracte. And the next big thing we're going to talk about is SQL, but let's take a break now. Thank you.